Hey everybody, Vade here. Sorry for not posting a video in over a month. There's just been a lot of stuff going on. Now, I know in the last video, the linearization video, I said that the next video would be on the Newton-Raphson method. But I feel like this video is something that I could just do a lot quicker. So I'm just going to get this video out of the way because I think it's pretty cool. And you can tell by the title, this video is how we can use Euler's formula, which we proved in one of the understanding, not memorizing videos. So you can go try to find where that is. It's in that playlist. We used the Maclaurin series for e to the x, sine, and cosine in order to figure out Euler's formula, which, if we can recall, is e to the I times theta equals to cosine of theta plus I sine of theta. It's very beautiful, because with that, we can then get Euler's identity, which is e to the I pi equals to -1. Okay? So very cool stuff. But how can I get the sum and difference formulas for sine and cosine with this? Well, first of all, we have to kind of play around with this formula a little bit. So we know that when we think about sum here, like let's say we're trying to find the formula for cosine of a plus b, and we're trying to find the formula for sine of a plus b. Okay, so let's kind of toy around a little bit with the idea of a plus b being in the argument here for both sine and cosine. So let's let theta equal to a plus b. Let's try that. Let's see what happens. So if we let theta equal to a plus b here, let's just substitute that in. E to the I times theta, which is just a plus b, don't forget parentheses, equals to cosine of a plus b plus I sine of a plus b. Great. So now we can, use the distributive property here on our e exponent here. So we could do I times a plus I times b. So let me write that down. E to the I times a plus I times b equals to cosine of a plus b plus I sine of a plus b. Okay, and now using properties of exponents here, we can split this, using the same base of e, we can split this into multiplication. So we can do e to the IA times e to the IB, right? Properties of exponents. I made just one of my first ever videos on this channel. It was going over the properties of exponents. If you're confused, go ahead and watch that. Hopefully you're not. So then this then equals to cosine of a plus b plus I sine of a plus b. Okay, and you're probably like, okay, Vade, how is this? This doesn't look like it's working. Well, wait. You see this cosine, or e to the IA and e to the IB? Doesn't that kind of fit the form e to the I theta, where theta is a and then theta is b? Well, let's play around with that. So e to the IA would just be cosine of a plus I sine of a, right? E to the IB equals to cosine of b plus I sine of b. Well, let's substitute that in here. So e to the IA, that's just the same as cosine of a plus I sine of a. And then e to the IB is just cosine of b plus I sine of b. And then this then equals to cosine of a plus b plus I sine of a plus b. So let's go ahead here and do the multiplication on the left side here. So we get cosine of a times cosine of b plus cosine of a times I sine of b plus I sine of a times cosine of b plus I squared sine of a times sine of b equals to cosine of a plus b plus I sine of a plus b. Hope I'm not going to run out of room here. So now we see I squared here. Hopefully you know that I squared is -1, right? Because if I equals to the square root of -1, you square both sides. I squared equals -1. So let's rewrite this as cosine of A cosine of B plus cosine of A times I sine of B plus I sine of A times cosine of B. And then since I squared is -1, that'll just be negative sine of A sine of B equals cosine of A plus B plus I sine of A plus B. So, you know what? I'm going to do a quick rearrangement for a third time. I'm going to move this I here to the front, right? Because commutative property, I can just move this I here to the front. So I'm just going to write this as cosine of A cosine of B plus I cosine of A sine of B plus I sine of A cosine of B minus sine of A sine of B equals to cosine of A plus B plus I sine of A plus B. Okay, so now what I'm going to do here, look at these two terms right here. I'm going to factor out an I, okay? So what I'm going to do here, and then I'm also going to just put this next to this. So I'm going to have cosine of A cosine of B minus sine A sine B plus I. Then I'm going to factor out the I here. Then we get cosine of A sine B plus sine A cosine of B. And hopefully you're seeing what's happening here. Then this would equal to cosine of A plus B plus I sine of A plus B. So let's kind of match things up here. We have a cosine A minus cosine A cosine B minus sine A sine B. And we have a cosine of A plus B here. And then we have an I. We see an I here. Then we have a cosine A sine B plus sine A cosine B equals sine of A plus B. So if we kind of match things up here, right, because we rearrange this into a certain order, we can just set these terms equal to each other, right? We see this would go with this, and we see an I here, and so then this would go with this. So then we can say, therefore, cosine of A plus B equals to cosine A cosine B minus sine A sine B. And then we can say sine of A plus B equals cosine A sine B plus sine A cosine B. This is written a little different than how you'd usually write it. I would usually write it as sine A cosine B plus cosine A sine B, but it doesn't really matter. And these are indeed correct. If you want to see how I got these through a more traditional kind of geometric approach, I made a video on that, on proving these formulas and understanding, not memorizing. It is a pretty informal proof, but it kind of works. It's also one of the more unique proofs out there that I think a lot of textbooks should try to include, instead of just saying, oh, it's out of the scope of our textbook. And then, of course, proving tangent of A plus B, super easy. Just, use your quotient identity. And then proving the difference is just doing A plus negative B. So once you have these two, you can obviously prove the rest. But yeah, hopefully you enjoy this video. It's very, very interesting. I got this out of the Art of Problem Solving calculus textbook. Very nice. If you forget your angle sum formulas, you could just remember Euler's formula and you could get them out of this. It's a really, really cool way of getting the angle sum formulas, because these are the angle sum and difference formulas are often the ones that people forget the most out of all the trig identities. It's always these. Maybe the half angles as well, but these are also these are the big ones that people forget the most. And so just knowing this simple Euler's formula can help you out a lot. Okay, it's also a very beautiful formula. You can get a lot of stuff out of this guy, like Euler's identity, most beautiful equation in all of mathematics. So hopefully you enjoy this video, and I'll see you guys on the next one. Hopefully I can talk about Newton-Raphson next, or I'll probably try to squeeze a bit more of interesting videos before I get to that, which is also interesting, but I want to get the quick ones out of the way, because it's been a while since I've posted. I want to get some stuff out there. So yeah.